Welcome to part 4 of module 1. Here we're going to cover the theory of diesel cycle, which models the compression ignition engine. The prereq for this is part 3 of module 1, where we covered AutoCycle. So we'll discuss this diesel cycle, air standard diesel cycle, in relation to what we have done for AutoCycle. So let's start with this animation, that is the diesel cycle animation. I'll go take you straight there. Animation module, IC engines, CI engine. The CI stands for compression ignition, and as you can see, a lot of it looks similar to the spark ignition engine. Let me just pause the animation and step you through it. So as in spark ignition engine, you see the bottom dead center, top dead center. These definitions are the same. The bore of the cylinder, the displacement volume, the volume swept by the piston, the clearance volume, the smallest volume after the gas is compressed. All of these are the same. The compression ratio, the definition is the same. It's the maximum volume divided by the minimum volume. It's called the volumetric compression ratio. Where the cycle differs, a compression ignition differs from a spark ignition, is that in compression ignition, the air is, after the air intake, the air is compressed and no fuel is sprayed into the incoming air. Instead, after the compression takes place with a much higher compression ratio than in the gasoline engines, the air becomes very, very hot. At that time, fuel is injected into the cylinder. The air is so hot at the end of compression that the fuel auto ignites, and that's why the engine is called compression ignition. Well, let's go step by step through processes, then it will become a little more clearer. So let's first go to the intake stroke. It is exactly the same as before. During the intake stroke, the intake valve is open and the piston goes from top dead center to bottom dead center, drawing in outside air. So the state during the in the PV diagram, probably you will see the state, the thermodynamic state doesn't change, the total volume changes, but the pressure is assumed to be the same as outside air. So state 0 and 1 thermodynamically are the same. That's why in the TS diagram it's in the same state. If we drew P and small v, specific volume, 0 and 1 will be the same. So intake stroke is identical between AutoCycle and diesel cycle. What about the compression stroke? Same here. In the compression, during the compression from bottom dead center to top dead center, we can neglect any heat transfer because the compression is very rapid, and we can neglect the entropy generation. There is no friction inside, and as a result, we can say during the compression is isentropic, just like as in the AutoCycle. So therefore, we can write, okay, we'll come back to this screen. Okay, let's start building the TS diagram as we discuss this. So as a result, we can draw the TS diagram for the diesel cycle as from state 1 we go to state 2. So this is isentropic, and why the compression process is isentropic? As you recall from our AutoCycle discussion, the entropy equation for a process is this, and if there is no heat transfer, no friction, this reduces to delta S equals 0, or mass times S2 minus S1 equals 0, which tells us that S1 must be equals S2. So this is, as soon as you know S1 equals S2, we can apply the PG model isentropic relationship, equation 11 of PG model. Again, you must be familiar with this from our AutoCycle discussion. Table J has all these equations listed. So therefore we can say, it's like, for instance, T2 over T1 will be V1 over V2 to the, I believe it will be K minus 1. So if the compression ratio is R, so the formula remains the same for isentropic compression. And of course, the compression ratio for diesel cycle is much higher, almost twice as much as that of an Otto cycle. Going back, so after the compression stroke, what happens is that fuel is sprayed and the fuel as the fuel is sprayed, the fuel starts burning because the temperature is so high at state 2 that fuel immediately starts burning. However, unlike the Otto cycle where the fuel is already vaporized and the combustion is almost instantaneous, the fuel droplets here, the small droplets of the fuel, they cannot burn instantly. As a result, as the fuel burns, the piston cannot be assumed to be at the same location. Well, you can understand why the fuel droplets take longer to burn, because think about how combustion takes place. Even though we haven't done combustion, which is in chapter 13 yet, it's easy to understand. Think of a fuel droplet. A small droplet of fuel, as it burns, what happens is that there's a fire around this spherical fuel droplet. And as a result, so suppose here's a fuel droplet and there's a fire around it. So what happens, the heat from this flame comes to the fuel droplets and vaporizes, fuel vapor comes out. So this is all fuel vapor here, and oxygen from surroundings comes, and that's where fuel and oxygen reacts, creating the flame. So obviously it cannot be instantaneous because fuel has to vaporize and then it has to react with oxygen in the air, surrounding air, and this process takes time. So the smaller the droplets, the large number of droplets, the better it is. That's why fuel injections has is very complicated design to make sure the fuel breaks up and there's a big spray of droplets. Anyway, as the fuel burns, it takes a little time. That's why we cannot assume that the volume is constant. In diesel cycle, but think of what happens. As the fuel droplet burns, a lot of heat is released. So when there is a heat release, you can understand the pressure will have a tendency to increase because the temperature is increasing. However, because the piston has already begun its downward motion, the volume is increasing. So if you apply PV equal RT, imagine what's happening. Temperature is going up and the volume is increasing. So as a result, pressure is somewhat remains constant. It's a good assumption to assume as the heat addition takes place, pressure remains constant in a diesel cycle. So that's an assumption, but that's pretty close to reality. So what happens? We are spraying fuel, and in that time the pressure remains constant is our assumption. And by the way, the fact that droplets takes time to burn, you can see that any diesel car or in a diesel truck, if you suddenly put a lot of fuel, you'll find that the diesel truck will have black smoke coming out. Why is that? Because these droplets haven't completely burnt yet, and yet we have too much fuel to burn within the little bit of time, and when the exhaust is thrown out, there are still fuel droplets left. They're all charred, turned into soot, and that causes the black smoke, which you don't see in a gasoline engine. Anyway, that's an aside. So we'll assume that the fuel when fuel is added is same as adding heat at constant pressure. So that's the chief difference between a diesel engine and an auto engine. In an auto cycle, the volume remains constant when the heat is added, and in a diesel cycle, pressure remains constant when heat is added. However, when heat is added, it doesn't continue for a long time, and the heat addition or the spray stops at a certain point. It's called fuel cutoff point. So the volume at that time, the cutoff volume, the volume of the cutoff divided by the clearance volume is called the cutoff ratio, RC. So that's a new parameter. So an engineer, when he's designing a diesel engine, will choose a certain RC. In other words, suppose RC is 2, which means as the volume doubles from the smallest volume to twice its volume, the fuel spray stops. So that will provide us a condition of finding state 3. Either the maximum temperature is supplied or the cutoff ratio is supplied. So as the process continues from 2 to 3, constant pressure heat addition takes place. The amount of our Q in takes place, and we can express that very easily by going to analyzing a process, a constant pressure process. So the heat addition process on the TS diagram, if we go add that, it will be a constant pressure line. And recall that a constant pressure line is less steep compared to a constant volume line. So from 2 to 3, the heat that is added happens at constant pressure. So to derive a formula for that, if you recall, we have done that before in our chapter 5 review. We have shown that Q in will be M H3 minus H2, which is M Cp T3 minus T2. In other words, this formula comes about from the fact that delta U equals Q minus W boundary, and in this case, as heat is added, there is boundary work done. In other words, work and heat are both transferred during the heat addition process, and therefore this becomes a better formula to use. We derived that. So knowing how much heat is added, one can find T3, or knowing T3, one can find how much heat is added. Let us continue with the next process. So now what happened? We have added fuel, or in the case of diesel cycle, in a compression ignition engine, we are adding fuel. In a diesel cycle, which is modeling the compression ignition engine, we'll assume heat is added. So the heat addition stops when we reach state 3. Then what happens is that the air is still very hot, and at a very high pressure at state 3, it expands isentropically, just like in an AutoCycle, to state 4. At state 4, we have reached the bottom dead center. Therefore, the volume is exactly same as state 1, because at state 1, the piston was also at bottom dead center. Therefore, state 4 and 1 must have the same volume, and because the mass is the same, specific volume is the same. So therefore, 3 to 4 is our power stroke. Actually, the power stroke starts from 2 really. 2 to 3, if you notice, is a partial power stroke and heat addition stroke, and 3 to 4 is an isentropic power stroke, which exactly follows the isentropic formula of a perfect gas. So isentropic formula for perfect gas links our 3 to 4 just like as in an AutoCycle. So the formula there would be of course, equation 11 again from table J. And we notice that, so what happens in an isentropic expansion is that the temperature at 3, temperature at 4 are related by volume at 4, volume at 3 to the power K minus 1. But notice, unlike the AutoCycle, we cannot write volume over 4 equal these volumes. Volume 1 over 2 is R, our compression ratio, correct? But we cannot write that is same as V4 over V3. So what is V4 over V3? So V4 over V3 equals, V4 is same as V1 so we can write this like this, and V1 over V2 we divided and multiplied by V2. V1 over V2 is R, and what is V2 over V3? If you recall, V2 and V3, if you go back to the diagram, you will see V2 is here's the piston. What is V2? It is the smallest volume when the piston was here. This is the clearance volume. And what is V3? When the fuel injection stopped, when the heat addition stopped. So that this total volume is V cutoff. So therefore V3 is V cutoff and V2 is V clearance. So this is 1 over RC by definition. So this is an important point. So therefore, to find the temperature at 4, you must know RC and R both. So that's where the diesel cycle analysis primarily differs from the AutoCycle analysis. Everything else is almost about the same. If we go to finish up, now as you can see, the power stroke is the same, and of course the last process is the constant volume heat rejection. Really what happens is there's a blow down, the piston, the exhaust valve opens, and as soon as it opens, hot gases escapes. And in the diesel cycle, we mimic that by saying from state 4 we come back to state 1 through instantaneous heat rejection. This is modeled exactly as in AutoCycle. There is no difference there. So the Q out here that takes place can be written as, so Q out must be equals mass times U4 minus U1 CV T4 minus T1. So now that we know the temperature and Q in and Q out, we can find net work equals net heat, which is Q in minus Q out, and therefore thermal efficiency can be found from Q net over Q in. Notice that finding W net directly is more difficult in a diesel cycle. Why? Because there is work produced during the power stroke as well as during the heat addition stroke, because pressure remains constant. Take a look. The piston is moving while I'm adding heat. So as the piston moves, it pushes the connecting rod, making the crankshaft move. So power is produced from 2 to 3 as well as 3 to 4. And that becomes clear if you look at the PV diagram. 2 to 3, note there is an area underneath that, and from 3 to 4 there is some area underneath that too. So from this entire area is really the work done as the piston, during this much of the work is done during the heat addition process, and the rest of the work is done during the rest of the power stroke isentropic process. Again, when we solve a problem involving a diesel cycle, we will see how to find the net work. It's easier to just evaluate heat in and heat out rather than finding explicitly all the different work terms. Well, now that we have covered both the Otto and diesel cycles, I want to show how we can predict how a particular change in parameter will affect the thermal efficiency or the net work output. Let's start with first an AutoCycle. Remember, in AutoCycle, these are all constant volume lines. isentropic compression, constant volume heat addition, isentropic expansion, and constant volume heat rejection. Now suppose the question is, okay, so let's first draw exactly where the heat is added and heat is rejected, because that will play a vital role in what we are discussing. We already know that heat is added here and heat is rejected from 4 to 1. Again, this is an AutoCycle. Suppose the question is, let's say we increase the temperature, the highest temperature of the cycle. Will it affect the efficiency or the network? Well, everything else remaining same, compression ratio remaining the same. Let's draw it in a different color. So we'll make this a habit of ours. So we are altering the cycle. We are increasing the maximum temperature. So 3 will move up along the same line. Let's say to 3 prime. So to complete the cycle, the expansion stroke, power stroke, isentropic stroke will go down like this. And this is a constant volume line, so this will be our 4 prime. So the new cycle is 1, 2, 3 prime, 4 prime. As you can see, the net area is higher. Therefore, so the question is, if Tmax increases, if Tmax increases, this will be our symbolic way of saying that. If Tmax goes up, it implies that Wnet must go up, right? Because the net area is higher. What about the efficiency? Well, that becomes a little bit tricky. How do you figure out the efficiency without really solving the problem? How can you graphically conclude what happens to the efficiency? One way to think of what would be a Carnot cycle look like? An equivalent. We know that a Carnot cycle, we can take a lot of lessons from a Carnot cycle. In a Carnot cycle, heat addition takes place at constant temperature. Power stroke takes place at constant entropy. Heat rejection takes place at constant temperature. So a Carnot cycle looks something like this. Again, it is well covered in chapter 7 in your book. So I'm not going to go over the entire thing here, except to say that, look, in a Carnot cycle which looks like this, we know the heat addition takes place at TH and heat rejection at TC, resulting in a thermal efficiency of 1 minus TC over TH, which we all know very well. Now, yes, an AutoCycle may not look like a Carnot cycle, but you can approximate it by saying, you know what, the original cycle 1, 2, 3, 4, where is the heat addition taking place? We can say, you know, approximately that this is the equivalent temperature. So we'll call this TH bar, kind of an average temperature of heat addition. And the heat rejection, we'll call this is my TC bar. So the efficiency is 1 minus approximately of the AutoCycle is 1 minus TC bar over TH bar. In other words, even though the efficiency formula is complicated for AutoCycle, it's not simple like a Carnot cycle, we are making an equivalence here. That in Carnot cycle, the temperature of heat addition is constant, TH, whereas here an approximate, an equivalent temperature, kind of an average temperature. We won't bother about finding exactly what the average. It'll be somewhere between state 2 and 3, T2 and T3. Now what happens to the blue cycle? To understand what happened to the blue cycle, the modified cycle, we can say, you know what, efficiency of the thermal efficiency of the AutoCycle becomes 1 minus, it'll be again TC bar over TH bar. But what can we say about the TH bar? Would you agree in the new cycle the heat addition takes place from 2 to 3 bar? As a result, TH bar is slightly raised. So we can say, aha, look, TH bar is higher. So will that increase the efficiency? The first thought, yes. But no, don't be so sure. Look at TC bar. In the modified cycle, TC bar is also raised. So when both the numerator and denominator have gone up, we are not certain what will happen to the efficiency. So if the question is, in an AutoCycle, we raise the temperature, maximum temperature of the cycle without changing the compression ratio, the answer would be, well, that is going to raise the net output because you can see the extra area added, but it is not going to affect the, we don't know how it will affect the efficiency. We are not sure about it. Obviously, if in a cycle you find that TC bar is reduced and TH bar is increased, or a combination of the two, then efficiency will surely increase. And I want to show that to you by another what if experiment. Suppose we say in an AutoCycle again, the compression ratio is increased without changing the maximum temperature. So let's draw the cycle in black first. So again, it's an AutoCycle, and this time so this is a red cycle, let's call it. With red color, let's represent the heat addition and heat rejection. So the Tmax is not being changed anymore. We keep maximum temperature the same, but we are raising the compression, the volumetric compression ratio. So let's draw the blue cycle. So the thought experiment of state 1 is the same, but this time the isentropic compression takes us to, let's say, 2 prime. And of course, after 2 prime, we have to draw a new constant volume line, which will be something like this. And the maximum temperature not changing, this will be our 3 prime. Does that make sense? From 3 prime, isentropic expansion will bring us down, and we have to meet this constant volume line. So our new cycle will be 1, 2 prime, 3 prime, 4 prime. Heat addition will take place from 2 prime to 3 prime, and heat rejection from here to there. So now let's compare the efficiency. In case of blue cycle, we can say the average temperature is somewhere here. This is our TH bar, and somewhere between 1 and 4 prime, this will be our TC bar. Okay, let me draw it on this side and it can be clearer. Does it make sense? What about the red cycle? In the red cycle, the heat addition takes place between 2 and 3. Notice 3 is same, whereas 2 is much lower than 2 prime. So on the average, the temperature of heat addition will be something a little bit lower. What about heat rejection in the red cycle? 1 to 4. 1 to 4. 1 is the same point as the blue cycle, but 4 prime versus 4, you can see that TC bar is probably slightly higher. So the thermal efficiency of the red cycle of the AutoCycle, 1 minus TC bar over TH bar, versus when we go to the blue cycle, at the thermal of the AutoCycle, 1 minus TC bar over TH bar, we can see for the blue cycle TH bar has gone up, whereas TC bar has gone down. So therefore we can conclude that the efficiency is going way up. And that was the conclusion from the formula, if you recall. That is, if the effective temperature of heat addition is increased, as in this case, you can say the efficiency, and plus TC bar goes down, or a combination of the two, that means thermal efficiency will increase. So look at the beauty of this Carnot analogy. So this is what is known as the Carnot analogy. And we are going to use that over and over again in the upcoming cycles, such as Brayton cycle, Rankine cycles, etc. Now notice that if someone says, what about W net? Well, is W net going to be higher in this modified cycle? We'll say, not so sure. We added this area and we lost this area. So therefore, you cannot say for sure. You cannot say the W net doesn't change, but you can see that it's not clear. But you know for sure, if I keep on increasing the compression ratio more and more and more, 3 prime will veer to the left, and the included area will become such a thin slice, ultimately going to 0. So if we keep on increasing the compression ratio, Yes, the efficiency will increase, but ultimately it will lead to very low power output. But the general conclusion is that in an AutoCycle, if you keep increasing the compression ratio, the efficiency goes up. But the problem is that why don't you keep doing that? If we keep going to a very high pressure, as you can see, at 2 prime, the temperature is way higher than at 2. And gasoline ignites very easily, especially when it is mixed with air. So the temperature at 2 prime can be so high that before you spark, the gas may ignite. And that's something very undesirable. We want to control when the ignition takes place to the spark. So that's why even though the efficiency is very high in a spark ignition cycle, in an AutoCycle, the efficiency increases with compression ratio. We practically cannot raise it, say after about 10 probably is the highest compression ratio you can go. In a diesel cycle, on the other hand, diesel doesn't burn so easily, so therefore you can go much higher, and as a result, the diesel cycle is really much more efficient, which you can compare again on the same token. I know I'm taking a little too long here, but I just cannot wait to make this point. So suppose someone says we have a TS diagram, and let's draw both this is an AutoCycle, and let's say the maximum temperature we are not going to change, and given that constraint, because the maximum temperature is based upon what the material can withstand, and this is our AutoCycle, how will our diesel cycle look like? So in a diesel cycle, same initial condition, but compression ratio is way higher. So this will probably be, let's do it in a different color. This will be the diesel cycle. And from 2, it is a constant pressure line. Remember that, right? So the constant pressure lines are much less steeper than constant volume line. So probably the line is like this. So as a result, look at the temperature where the heat is added in a diesel cycle versus where heat is rejected, as opposed to that in a gasoline cycle, heat is added generally at lower temperature. So based on where 3 prime is, you can show that the efficiency of a diesel cycle, because TC bar is going up, I shouldn't say equal, it's approximately equal, TC bar over TH bar. TH bar is lifted up in a diesel cycle. Here it seems like TC bar is also lifted up, but really 3 prime need not be so much to the right, it could be somewhere to the left. So TC bar actually doesn't change that much, it's about the same, and as a result, a diesel cycle has higher efficiency than an AutoCycle. Anyways, it will be interesting to always come up and discuss how a modification affects TC bar and TH bar, and which we are going to do a lot more in the future cycles we are going to cover.